In this video, we're going to take a look at Taylor and MacLaurin series. So previously, we have seen some applications of power series, but those applications and representations relied upon 1 over 1 minus x. So in this section, we're going to try to generalize that idea from the previous section in order to try to represent more functions as a power series. To do this, we're going to assume two things. First, that the Taylor function f of x, that the function f of x does in fact have a Taylor series representation about x equals a, and second, that f of x has derivatives of all orders. Moving on, we will suppose that f of x can be written as a power series. Then f of x is equal to c naught plus c1 x minus a plus c2 x minus a quantity squared plus, and so on, right? That is this power series, n equals 0 to infinity of c sub n x minus a to the n for all x where the absolute value of x minus a is less than r. So on some interval of convergence. Now, let's try to find a formula for these constant coefficients, c naught, c1, c2, c3, and so on. Let's see if we can find a formula for that. Okay, let's try that. So we're going to find a formula for those c sub n's. First, note that if x is equal to a, then we have f of a is equal to c naught plus, and let's plug in a into this up here. Well, if I plug in x equals a, then we get a minus a, so this term goes to 0. If I plug in a here, a minus a, that goes to 0. So, in fact, we just get 0. So f of a is equal to c naught. Okay. So we have a way to calculate our first coefficient, that's c naught. That's actually just f of a. All right. Let's see if we can do something similar for the others. Since f of x has a derivative, right? It's one of our assumptions we are making. So we have a function that is differentiable. Let's take the derivative. All right. Well, then f prime of x is equal to c1 plus 2c2 x minus a plus 3c3 x minus a squared. Right? I'm just taking the derivative of each one of these terms up here in our power series representation. Okay. Well, if we do that, then what do we get? Well, what is f prime of a? Well, this is c1 plus, and we plug in a into here. Oh, that's 0. And plug in a into here. Oh, that's 0 as well. And that's going to happen forever. So, in fact, we get c1 is just the first derivative of our function evaluated at a. Ah, interesting. Let's keep going. Then, f double prime of x is equal to 2c2 plus 3 times 2c3 x minus a plus 4 times 3c4 x minus a squared, and so on. Then f double prime at a is 2c2 plus, and then a bunch of terms with 0. Because if we plug in a into each of those terms, we're going to get those terms evaluating to 0 if we plug in x equals a. Okay, so in fact, C2 is the second derivative evaluated at a divided by 2. Huh. All right. Let's see if we can go a little further. One more. F triple prime of x is 3 times 2 times C3 plus 4 times 3 times 2 times C4, x minus a to the first, plus so on. So what is f triple prime evaluated at a? Well, that is 3 times 2 times C3 plus, and then we plug x equal to a into the rest of these terms. We get a bunch of zeros again. So we get C3 is equal to f triple prime evaluated at a, all divided by 3 times 2. Well, hopefully we can see a pattern now. Because that pattern, it turns out, is the following. In general, we see that C sub n is the nth derivative of f evaluated at a divided by n factorial. All right, and if we adopt the convention that 0 factorial is 1 and the 0th derivative of x is just the original function, if we adopt both of those conventions, then this remains true for n equal to 0, so for C naught. All right, this leads us to 2 definitions, and that's where we'll end this video. Write these 2 definitions down, and then in the next video we'll go over a couple of examples using all of this. The Taylor series of the function f at a is... So we take f of x is equal to the power series, or what we call a Taylor series, from n equals 0 to infinity, of the nth derivative of f evaluated at a over n factorial times x minus a to the nth power. And if we write out the first few terms of that, that is f of a is for the first term, right? We plugged in n equals 0. So n equals 0 here, x minus a to the 0 is 1. 0 factorial, we define that to be 1 up here. And the 0th derivative, we define just to be the original function. So it's the original function evaluated at a for the first term. Plus f prime of a all over 1 factorial times x minus a. That's the second term. The third term is the second derivative of our function evaluated at a over 2 factorial times x minus a squared, and so on. Okay? And we have a similar definition here for a MacLaurin series. So the MacLaurin series is the special case a equal to 0. So, the MacLaurin series is of f of x is n equal to 0 to infinity of the nth derivative of f evaluated at 0 all over n factorial times x to the n, right? Because x minus a to the n is what we normally have, but a here is 0, so we just get x to the n. And the first few terms of that are f evaluated at 0 plus f prime evaluated at 0 all over 1 factorial, which is just 1, times x, plus f double prime evaluated at 0 all over 2 factorial, which is just 2, times x squared, and so on. Okay? And that is our MacLaurin series. And we're going to use those in the next video to write out functions for, or write out power series, or Taylor series or MacLaurin series, for some special functions.